So imagine you're a scientist in the late 1800s. You know that light acts like a wave, and pretty much all the waves you study need a medium to travel through. Sound waves need air, ocean waves need water. So what exactly is light traveling through in the vast vacuum of space? Well, at the time, everyone basically agreed that space was filled with this invisible stuff called the luminiferous ether. But that assumption led to a massive, glaring question. If Earth is hurtling through space, plowing through this stationary ether, shouldn't we feel an ether wind? And more importantly, shouldn't that invisible wind push and pull on light, making it travel just a tiny bit faster in one direction and slower in another?
Welcome to today's Explainer. We're going to unpack the Michelson-Morley experiment, which is often called science's most famous successful failure. Now, the word failure is key here. We usually think of scientific progress as the series of brilliant, calculated successes, right? But today, we're going to see how an incredibly precise experiment, designed by two brilliant minds to measure something unfathomably tiny, ended up failing so spectacularly that it literally broke physics and completely reshaped our understanding of the universe.
All right, let's start with Section 1, the Great Ether Mystery. To really get the immense scale of what happened, we have to understand exactly what physicists Albert Michelson and Edward Morley were actually hunting for back in 1887. They were trying to prove once and for all that the ether existed by catching that ether wind we just talked about. Their logic was pretty sound. Just like a boat takes longer to go upstream against a river's current than it does going downstream, a beam of light should take slightly longer to travel against the ether wind than with it. But there was a major catch. The expected difference in the speed of light was incredibly small. We're talking about a microscopic fraction of a second. Standard 19th century scientific tools were nowhere near sensitive enough to detect a change that minuscule. If they were going to measure the effect of the ether on the speed of light, they couldn't just use a better stopwatch. They needed a totally new method, an instrument so precise it could measure changes at the scale of light waves themselves.
Which brings us to Section 2, splitting the light. To solve this monumental problem, Michelson invented a device of absolute, undeniable genius. He called it the interferometer. It's so beautifully simple that its core principles are still heavily used in labs all over the world today. If we think about how a modern setup works, it's actually the easiest way to grasp the concept. A laser fires a single, solid beam of light. That beam travels and hits an angled piece of glass right in the middle, a beam splitter. And it does exactly what it sounds like. It splits the light. Half the beam goes straight ahead to a mirror, while the other half gets bounced at a 90-degree angle to a different mirror. Those two distinct beams then bounce off their mirrors, meet back up at the splitter, and recombine to hit a screen at the bottom. It's basically an elegant, perpendicular racecourse designed specifically for light. The crucial part is what happens when those two beams finish their race and recombine. They create what's known as an interferomogram. Think of it as a pattern of concentric rings, usually called fringes, created when the split light beams interfere with each other. It looks a bit like a bullseye. If the two beams of light arrive at the exact same time, their waves align perfectly. But if one beam is delayed by even a tiny fraction of a single wavelength, the waves get slightly out of sync. When that happens, that entire bullseye pattern visually shifts. It's an incredibly hypersensitive light detector. Even with over a century of tech upgrades separating a modern laser from a 19th century light source, the fundamental geometry is exactly the same. You've got your light source, your beam splitter in the middle, and your two distinct paths traveling outward. The real genius of Michelson and Morley, though, was how they built it. They set this entire delicate apparatus up on a massive, heavy block of stone, and then floated the whole thing on a circular pool of liquid mercury. This completely eliminated any earthly vibrations, making sure the paths were perfectly pristine for the light's journey. So here is the core mechanism of the experiment. The whole idea was based on that hypothetical ether wind blowing as Earth moves through space. Michelson and Morley believed that if they gently rotated their floating stone apparatus, the ether wind would affect the beams differently depending on how they were oriented. One beam would have to swim against the current, right? So it should take slightly longer. And that tiny, tiny delay would cause those interference fringes on the screen to shift out of phase. All they had to do was rotate the table, watch the bullseye through an eyepiece, and measure the shift. Let's move on to Section 3, the most famous null result. Everything in the lab was perfectly calibrated. The math was completely sound. The global scientific community was literally waiting with bated breath for them to finally measure the ether wind. They spun the heavy stone table, they looked carefully through the eyepiece, and here is the major plot twist. The expected result was a clear, measurable fringe shift. The actual result, no measurable shift whatsoever. None. Zero. They rotated the apparatus again and again. They ran it at different times of day and even different times of the year, just in case Earth's orbit was playing tricks on the wind's direction. But no matter what they did, the light beams always returned at exactly the same time. The fringes never moved. In the science world, this massive, highly anomalous absence of expected data is famously known as a null result.
That takes us to Section 4, Einstein and constant light. This wasn't just a simple failed experiment in a basement laboratory. This was a full-blown crisis in physics. The null result completely shattered the existing laws of classical mechanics. I mean, if there was no ether wind pushing against the light, how was it traveling? And why didn't its speed change when the Earth's speed and direction changed? It forced a really uncomfortable rethink of physical reality itself. Ultimately, this spectacular failure proved two massive things. First, there is no detectable stationary ether, that invisible fluid holding the universe together. It just didn't exist. Second, and this is the really profound part, the speed of light is exactly the same in all directions. It is stubbornly, undeniably consistent no matter which way Earth moves or how fast it goes. Classical physics simply couldn't explain it.
What's truly amazing is how that failure became the foundation for everything that followed. Nearly 2 decades later, a young patent clerk named Albert Einstein looked deeply at this exact null result. Instead of trying to invent crazy new math to fix the broken ether theory, he just accepted the experiment's findings as a fundamental truth of the universe. He made it a core postulate of his 1905 special theory of relativity, stating that the speed of light in a vacuum is constant for all inertial observers. Michelson and Morley's failure to find the ether gave Einstein the exact bedrock he needed to completely rewrite the laws of space and time.
And finally, Section 5, Modern Marvels of Measurement. You might be sitting there wondering, why does an experiment from 1887 matter to us today? Isn't it just a cool piece of history? Well, it turns out that while Michelson didn't find the ether, the ridiculously precise instrument he invented ended up fundamentally changing the modern world. Because the interferometer can measure distances at the minuscule scale of light waves, it's absolutely vital to the tech we use today. We use it in semiconductor manufacturing to craft the microscopic chips inside our phones and laptops. We use it to test precision optical components and keep satellites perfectly aligned in orbit. And honestly, my favorite application, we use the exact same basic L-shaped setup in gravitational wave observatories like LIGO. Instead of looking for an ether wind on a stone block, LIGO uses massive interferometers with arms that are miles long to detect the tiny, tiny ripples in space-time caused by black holes colliding billions of light years away. So I want to leave you with this provocative question. How did the failure to measure a microscopic shift in light unlock the fundamental secrets of space and time? It's a powerful reminder that in science, there's really no such thing as a truly failed experiment, as long as your measurements are accurate. Michelson and Morley set out to map the invisible ether, but by finding absolutely nothing, they handed us the keys to understanding relativity, the cosmos, and paved the way for modern precision technology. Thanks so much for joining me on this explainer. Keep looking closely at the world around you and never stop questioning what you think you know.